Let me show you how to calculate the energy of an alpha decay. This is actually a fairly simple calculation to do. The first thing to do is to figure out what the decay, what the products of the decay are, right? And that's pretty simple. We already know how to do that. So uranium-232 will turn into thorium, which is element 90, right? At thorium-228, right? So this is another way to write the notation, right? Plus an alpha particle, okay? The next thing to do is to look up those masses, right? So here's the mass of the uranium, here's the mass of the thorium, and then for an alpha particle, we use a helium atom, okay? And this works. The helium atom takes care of everything, right? Here we have 92 protons and 92 electrons. Here we've got 90 protons, 90 electrons. And here we have 2 protons, 2 electrons, right? So that works. And then, you know, the neutrons all work out as well, okay? Then what we do is we just look at this. This side here, this combined mass, is going to be less than that mass. And the reason is that energy is given off, and energy has mass, right? And so if we give off energy, we give off mass, and therefore the right side has less mass, okay? So what we're going to do is we're going to subtract the right side from the left side, just like this. So the left side, okay, left side mass is 232.037131 U's, right? Well, what was that? That's a U. What happened to it? A U. Pretend it's just that, right? It's like, okay. And then the right side, I'm going to take a calculator and add those up. So 228.028716 plus 4.002602. Okay. 02871602876. Okay. Okay, and then the right side mass. Okay, when I add this number to this number, I get 232.031318. Okay, that's a 1. It got kind of lost on the way to one land, you know. Okay. Notice that this is less mass, yes, notably by that digit there, right? Okay. So where did that mass go? Well, I thought mass was conserved. Well, no, mass and energy are conserved. The difference turned into energy. So here's the difference, right? I'm going to subtract 232. So subtract those two. 131. And I get that the mass defect, right? And this is what it's called, 005813. Okay, this is called the mass defect. And defect is used here in the sense that we expect matter to be conserved, right? But matter in this case is turned into energy, right? And then all we do is we just multiply that mass defect by 931.5. And we're done. So I'm going to go times 931.5. And I get that the energy released is 5.4148, or with 4 sig figs, we've got that. And we have 4 sig figs because of this guy right here, right? And because I guess that number there also has 4 sig figs, right? So here's our answer, 5.415 MeV. Okay, so that's really not so hard. Just find what represent the right side, subtract the right side mass from the left side mass, and there you go, right? Now, just a little bit more about alpha decay. You know, why does it occur? It's only possible if you lose mass. Okay, if you lose mass, then that means that energy is released, and this is just a natural tendency. Rocks tend to roll downhill, right? So there's a natural tendency to reduce potential energy. And it only happens with large nuclei. Carbon does not undergo alpha decay, but uranium, thorium, all those giant ones do. And the reason for this is that a helium nucleus is actually fairly tightly bound. It's pretty, for the lighter nuclei, it's higher in general than the other ones here. So this graph here, this is one of the most important graphs in nuclear physics, right? This is, you take the binding energy and you divide by the mass number, okay? So it's binding energy over A, and we talked about that in the binding energy thing. This is how stable the nucleus is, right? These are the most stable ones right here, right? These guys are a little bit unstable. Here we can actually, I guess, split the nuclei apart and get them to be like this and release energy. And then here we can actually put nuclei together and release energy to make them more like this, right? So stars tend to, early on in their life, combine nuclei like this and release energy. This is the most stable atom right there, about iron or nickel or something like that, right? And what I'm saying here is that a helium nucleus is actually pretty tightly bound for a small thing. So mathematically, it's possible for, when you set up the reaction, right, for the products to have less mass than the parent, just because that's so tightly bound. You don't find any other nuclei really spit out in ordinary reactions, certainly not any spontaneous ones. Okay, we'll talk more about this curve later, but there you go.